How we doing, guys? So this is the next video from exercise 13b. We're on page 224 and we're looking at questions 9 and 10 in this video. Question 9 says a particle moves in simple harmonic motion through 2 points P and Q, which are 1.2 meters apart. There they are, P and Q, 1.2 meters apart. Its speed is the same as P as it is at Q. The only way that can happen if both of them are the same distance from, this is our mean position or our central position here, because the velocity is changing the whole time here, and the only time you get the same velocity is you come out here, on the way back you'll hit the same velocity, and then on the far side the same distance. It takes 3 seconds to go from P to Q, and then it takes 3 seconds again to go from Q back around to Q again. Okay? Find the period of the motion and find the amplitude. Okay, so first of all, if that's 1.2 meters between them, then the displacement is how far you are from your mean position. So that's going to be 0.6 meters at Q. Our period, T, this is just a counting exercise. From here till we get back to here again, moving right, let's say, it's going to take 3 seconds. Another 3 seconds, another 3 seconds, and then from here to here, just from the symmetry of the problem, is another 3 seconds. So it's going to take 12 seconds before we're back and moving in the same direction again. So t equals 12 seconds is the answer to that first part, and that always gives us omega, because we know that t is 2 pi over omega. So omega is 2 pi over t, which is 2 pi over 12 pi over 6 radians per second. Part 2 says find the amplitude. Okay, this is something we haven't seen yet, which is using this equation x equals a sine omega t. Okay, so we're using the sine version because we're saying if we start at here, so we're going to start our clock, as it were, here at the mean position. If you're starting at the extreme position, you use the cosine version. Okay, so starting at the mean position, you use the sine version, because sines start at 0 essentially. So x at Q, x equals 0.6, t equals, again, through symmetry, you can say that's 1.5 seconds it takes to get there from the center. And omega is constant throughout the motion. Omega never changes in simple harmonic motion. It kind of defines how fast the thing is moving, or how fast each period takes, I suppose. So we can come along and say, well, 0.6 equals A is what we want. Sine omega is pi over 6 times t. Okay, so, sorry, pi over 6 times 1.5, my apologies. Okay, so that's going to be A sine pi over 6 times 3 over 2 is going to be pi over 4. Okay, and that is, let's say that's 3 over 5 equals A. The sine of pi over 4, if you know it, that's 45 degrees, is 1 over root 2. And then multiplying through, you get 3 root 2 over 5 is the amplitude, which is 3 root 2 over 5. So 0.85 meters is the amplitude. For question 10, I've got parts of it ready to go here. The depth of water in a harbour is assumed to rise and fall with simple harmonic motion. On a certain day, the low tide has a depth of 13 meters, so that's our low tide there. At 12:58. Okay, there's your time along that axis. And the following high tide has a depth of 18 meters. There's the following high tide has a depth of 18 meters at 6:58 p.m. A ship requires a depth of 16.5 meters of water before it can leave the harbour. Find the latest time on that day that the ship can leave the harbour. Okay, so here's what we're looking at. Low tide 13 meters at 12:58. High tide 18 meters at 6:58. And you can see here tides follow a sympharmonic motion pattern. Okay, so what we're looking at is half a period of the tide. It'll be low again in another 6 hours. So straight away we can say that the period in this question is 12 hours. And as usual, that gives us omega, which is 2 pi over 12, or pi over 6 radians per hour, but we'll leave that as just pi over 6. So we've got period, we've got omega. Choosing what we use to model this. A sine wave starts at 0, so that's if you're starting at mid-tide essentially. Mid-tide, by the way, is at 15.5 meters, is the height of mid-tide, halfway between 13 and 18. So we won't use a sine wave. A cosine wave always starts at the extreme, but a positive cosine wave will start at 1. So that'd be like high tide. So we don't want that. We want this, a negative cosine wave. These are worth, by the way, if you have GeoGebra on your computer, just plug a few sine functions, sine of x and sine of 2x and sine of 3x in and see what you get. But here we have our negative cosine wave. Okay, also if you remember the period of sine, cosine, or a negative cosine, they all repeat every 2 pi radians. Okay, so our corresponding period out here is 2 pi. So we've kind of said 2 pi corresponds to 12 hours. And that lets us find our angular frequency up here as pi over 6. Now we'll come back to our unit circle in a second. So what's our equation? So we're saying A is minus, because we're starting at the extreme negative point, A is the amplitude cos omega t. So the amplitude here is how far we can stray from our mean position. Okay, so our maximum and our minimum is 2.5 above and below, excuse me, 15.5. Our range is 5 meters, so our amplitude is always half that range. So that's minus 2.5 cos omega is pi over 6 t. And x is how far we are at 16.5 meters is what we're interested in. So what's that? 13, 14, 15, 16.5, somewhere around here. And we want the latest point in the day. So I'll just point out that there's 2 times when the water is exactly at that level. So this is the time we're interested in. So when we solve our trig equation in a few minutes, we're going to have 2 solutions. In fact, there's an infinite set of solutions because the tide keeps coming in and out and in and out and in and out. But on that day, there will be 2 solutions. That's when we are at 16.5 meters is 1 meter above our mean point. So we say x has to be 1, and that's what we're trying to solve. So we'll say 1 over minus 2.5 is cos of pi over 6t, and that's the same as minus 2 over 5, or minus 0.4. Okay, so pi over 6t then is the cos inverse of minus 0.4. So if we come back here and look at our unit circle, again, that video on sine waves discussed the unit circle and this problem. Cos, if you'll remember, is our x coordinate on the unit circle. So we want our x coordinate to be minus 0.4. That happens here. That's the first time it happens, and that corresponds to our first time that the tide reaches the correct height, or the desired height. Around here is where our actual solution is going to be, which is what we're looking for. Okay, what angle do we need to go through? What does omega need to be to get that value? So let's go about doing that. Well, here, to find our reference angle, that's going to be the cos inverse of 0.4. And if you go to your calculator and make sure it's in radians, and you say the inverse cos of 0.4 is 1.15 radians, 1.16 radians. Okay, we want, well, let's look at the two solutions. Okay, so 180 minus that, or pi is 180 now that we're working in radians. So the inverse cos of that is either pi minus our reference angle of 1.16, or it's pi plus our reference angle of 1.16, pi plus 1.16. Okay, so what are our solutions here? We're getting pi over 6 t equals, so pi plus, that answer was 4.3, and pi minus that answer, pi minus, what was it, 1.16 is 1.98. Okay, multiplying through by 6 and dividing by pi, we're going to get t is 1.98 multiplied by 6 and divided by pi, or 4.3 multiplied by 6 and divided by pi. Okay, and hopefully we know that second answer is the one we're interested in. So let's find that first one first. Anyway, we've got it there. Multiplied by 6 divided by pi, that gives us 3.78 hours. Or this one here, 4.3 times 6 divided by pi, 8.21 hours. Okay, so that's 8 hours and 0.2123, so that is 12 minutes. Okay, you can maybe say 13 minutes. I have a feeling I did something funny here because I know what the answer is. So I think I just rounded something a little bit funny. So I'm going to say 12 minutes. After our low tide, okay, so after 8 hours and 12 minutes, that's the time we're looking for. Okay, so that's 8 hours and 12 minutes. After 12:58, and that is at 10 past 9 in the evening. That's the last chance, the last time the boat will have enough water to leave the harbour is at 10 past 9. Okay, so we'll leave it there. I'll see you in the next video. Bye bye.